Good morning, viewers. Welcome to this session. In this video lesson, I'm going to discuss about shear force and bending moment. In the last video lesson, we have gone through various fundamentals of shear force and bending moment. That means what is a beam and what are the types of beams we have, and we have seen there are different beams like cantilever beam, simply supported beam, overhanging beam, fixed beam, continuous beam, and combination beam. All these beams we have seen in the last class. And we have also discussed in the last video lesson types of loads that we have, that we will come across in shear force and bending moment. So in what are the various types of loads we have? We have a point load or concentrated load, uniformly distributed load or UDL, and uniformly varying load. And we have seen some practical examples also. And we have defined shear force and bending moment. If a beam is subjected to transverse loading means the perpendicular to the longitudinal axis of the beam, then it will be subjected to bending. So when the bending and shear force will occur, so we have to calculate the shear forces at various sections of the beam, and these shear forces and bending moments will help us in designing that particular beam. So from civil engineering's point of view, from mechanical engineering point of view, finding out the shear force and bending moment at various sections of beams is a very important factor when we take up the design. So in this class, in this video lesson, we are talking about cantilever beam, which is subjected to point load first, a single point load at its free end, and then we will say number of point loads at that means more than one point load at different sections of the beam. One numerical problem we will see, and after that we will go through what we call, if time permits, we will go through cantilever beam with uniformly distributed load over the entire span. This is the plan. Now I have a PPT for this, and I would like to share that. Through that, I would like to explain. So here we have shear force and bending moment of a cantilever beam, of cantilever beams. If you take a single beam, then what if it is subjected to various forces? First of all, we'll look into point loads. My name is Anand Padavala. I am a senior faculty member in the Department of Technical Education. That means in polytechnics. So of Telangana government. So let us start with the shear force and bending moment for a cantilever beam, which is subjected to point load first. So cantilever, first of all, what is a cantilever beam? So we have seen in the last class that cantilever beam is a beam which will have two ends. One is a fixed end, the other end is a free end. So there will be, one end is completely free and the other one is fixed. So such type of beam is called a cantilever beam. If at all we want to give a proper definition, here is a definition for a cantilever beam. A cantilever or cantilever beam is a rigid structural element which extends horizontally, generally it will be horizontal, and is supported at only one end. So this beam will have a support only at this end. So this is the prime quality of or prime characteristics of a cantilever beam. So typically it extended from a flat. That means generally when it is extended from a flat or a vertical surface such as a wall to which it must be firmly attached. That means fixed means it should be firmly fixed. Either it can be a flat or it can be a vertical surface, whatever it may be. So this is a cantilever beam. Let us see some practical examples where we will come across with the cantilever. Best thing is in civil engineering, we can see the beam here. See here this beam on which a load is given. This load is given on this beam. This beam, if you see, this end is a free end and this is a fixed end. And this fixed end is connected to one more pillar, one pillar here. So this is an example of cantilever beam. We'll go through one more example. Here is this is a car shed or car parking or a vehicular parking place. So if you see, this is a beam. These are the beams. So if you see, take this beam, this is a cantilever beam. This end is free, whereas this end is a fixed to this pillar. So like this, we have different cantilever beams on which the load is there, so it will bear. This is what a cantilever beam. Now, so we will go through cantilever beam with a point load at free end. So now we are starting the real subject. So how to draw shear force and bending moment diagrams for a cantilever beam with a point load at a free end. If you take here, this is a cantilever beam. So consider a cantilever beam AB of length L, the entire span is L, and a fixed end is A here, and a free end is B. And this is fixed firmly on the surface. So A is a fixed end, B is a free end, and the length of the span, length of this beam is L, and a point load or a concentrated load is there at the free end. That means it is carrying a point load capital W at its free end B. So our intention is to draw shear force and bending moment diagrams for this. So in order to draw the shear force and bending moment diagrams, first of all, we have to find out the shear forces and bending moments at various sections of the beam. Then it will be easy for us to draw the shear force and bending moments. Now, shear force. So consider a section X at a distance small x from free end. So we will consider a section. This is the section, and this section is small x distance from B. So from B to X is x small x, and from X to L, X to A is L minus X. So this is how. Now, let us the shear force at X, that means at this section, if you want to find out the shear force at this section is, let us say, Fx, and also bending moment at this section is Mx, let us suppose. Now, what is SF? Shortcut, we will call it as shear force as SF. So to save the time, we know the definitions. In the last video lesson, we have defined shear force or shear force at any section of a beam. If you want to find out what is a shear force at any section, it is the resultant force acting on right or left portion of the section. For example, if I want to find out the shear force at this section, I have to consider either left side or a right side. Any side we have to take, and we have to calculate the resultant force on either side. You have to take either left or right. So if I take this side, I will have a force here. So the resultant force will be W only. If I take on the left side, here you will have a reaction. Reaction force is exactly equal to the single force here because it should balance. Therefore, reaction. And this reaction, what is the resultant, that we have to calculate. So basically, shear force at any section is the resultant force acting on the right or left portion of the section. Now consider the right portion. For our convenience, I am taking the right portion only, not the left portion, because I have not calculated the reaction here. So I know the forces here. Therefore, I am taking it as a right portion of the section. Right portion of the section means from this X to B. This is the right portion of the section. Now, what we have to do as per the definition of this shear force at this section, the resultant force on the right portion of the section. What is the resultant? How many forces are there in the right side? We have only one force, that is W. Therefore, what will be the resultant when only single force is, that itself is a resultant force. So, the resultant force here is W, capital W, downward direction, because it is acting downward direction. So, what is the resultant force in this section? Is the right side of the section is W downwards. So therefore, as for the definition of the shear force at any section, shear force at the section X is nothing but Fx equal to plus W. Why we have taken plus W? Because when it is downward direction, in the sign convention in the last video lesson we have seen, if you take right side of the portion, then if it is downward, we have to take positive. If it is a left side, if it is the resultant force is in the upward direction, then you have to take positive. And in the right hand side, if the resultant is in upward direction, then you have to take negative. In the left hand side, if the resultant force is downward direction, we have to take negative. These are the sign conventions to draw the shear forces and bending moment diagrams, and to find out the shear forces at various sections. And the shear force will be constant all the section of the cantilever. For example, if I take X is here, we have left hand side only one force, right hand side. At here, if I take, still we have only one force. Therefore, there won't be any change in the shear force till then, because only single force is acting here. To my right hand side, there is only one force is acting. If you take any section between A and B, only single force. Therefore, the shear force will be that force only acting downwards, and there is no other load is there between A and B. Therefore, the shear force will be constant throughout the span from A to B. This is what we have. So now, hence, a shear force diagram of the beam is shown below. This is the shear force. So, if you take at B, it is plus 4W. If you take here, it is plus W. If you take here, is plus W. Therefore, if at all we want to draw, it is a constant. That means plus W. This is the baseline. If at all we want to draw we have to give a W here, and it is a constant. Therefore, it will be here. So, if we have a reaction here, W, when it is moving upward, it should be W, and it is constant till here. When the W is acting here downwards, it should match with the baseline. This is a shear force diagram of a cantilever beam with a point load at a free end. So this is what? This is a load diagram, and this is a shear force diagram. Now, we will talk about bending moment. When, if at all we want to draw bending moment diagrams, so first of all, we have to understand we have to calculate the bending moments at various sections of the beam. Now, first of all, let us see what is a bending moment. See here we have the same figure. So, what is a bending moment? In the last video lesson, we have defined bending moment at any section. Bending moment at any section of a beam is equal to the algebraic sum of moments of forces acting on either side of the section. There are, suppose I am talking about this X section. So there will be two sides, left side, right side, and a left side. So if you take algebraic sum of all the forces in this section about moment about this point, that means at X, moment about X, if you take algebraic sum of all these things, then it will be the bending moment at that section. Or otherwise, if you take left hand side, whatever the forces are there here, whatever the moments they will make with respect about that point X, Then about this point x, that is about this section, then the algebraic sum of such forces is called the bending moment at that section. So let us consider the right hand side section, because the force is here, therefore it is easy for us, no need to calculate the reaction here. Therefore consider the right hand side of the section x. Now BM at x equal to, how to calculate? So first of all, what we have to calculate? We have to calculate the moment of the forces in this. First of all, how many forces are there in this right hand side of the section x? There are only a single force, that is W. And what moment it will make about this x? So how to find out the moment? Moment is nothing but the force into its perpendicular distance. The force is W and its perpendicular is x. So the bending moment is W into x, because W is the load and x is the perpendicular distance. The load is acting from x. Therefore, bending moment at section as per this definition is equal to Wx. And we have given here a minus sign. Why minus sign is given? This moment is making a what kind of moment it is making? See, if you see, it is making a clockwise direction. Clockwise. The moment is clockwise direction. So right hand side clockwise direction, you should take it as a negative. Or otherwise, if you consider this one, what it will make? It is bending like this. For example, this is scale. It is bending like this. When it is bending like this, it is a convexity at the top. So it appears like a convex shape. So when it appears convex in the top, then we should take negative, or we will call it as a hogging also. So that's why we have taken negative sign. So the total bending moment at x is equal to mx equal to minus W into x, because only a single force is there. Now, so clearly it is indicative that bending moment is proportional to distance from free end. For example, if you take, I want to take a section here, then the bending moment is proportional to x. When x is more, the bending moment will be more. When the x is less, then the bending moment will be less. Of course, it will be either positive or negative, depends on the clockwise direction or anti-clockwise direction. But the magnitude, if we take, it will be increasing if the x is increasing. Therefore, it is proportional to a distance from free end. So, therefore, mx, that means bending moment x equal to mx equal to minus wx. Suppose I want to find out bending moment at b. If at all I want to find a bending moment at b. At bending moment b, we have x equal to 0. Bending moment means x value is 0. So x value is 0 minus w into 0 is 0 only. So bending moment at b is 0 because x is 0. Now, bending moment at L, that means A. Bending moment when x equal to L, that is at A, if at all find out, bending moment equal to minus W into x. In x place, we have to substitute L because x equal to L here. Therefore, bending moment at this section at A is minus WL. Bending moment at B is equal to W0, and bending moment at MX, that is at x equal to minus WX. This is how we have to calculate the bending moment. So hence, what does it mean? It follows the straight line law. Straight line law means y equal to mx plus c. So that means it is a straight line. It depends on the x. Here parameter is x. If x is more, then the bending moment will be more. So whenever we draw bending moment diagrams, when we are talking about free end at a point load, when as far as the point loads are concerned, we have to draw straight lines from one point to the other points. Whereas in shear force, you have to draw constant lines, that is parallel lines. Whereas here, you have to draw straight lines because it is following a straight line law. So now the bending moment diagram as shown here. This is a load diagram. This is shear force diagram already seen. Now bending moment. How we have drawn? Here bending moment is 0. Here is Wx. Here is W into L. So what you have to draw? You have to join this point. This, and this. All these things you have to draw. And this is the baseline. Below the baseline we have to draw because it's a negative sign. Why negative sign? Because the convexity at the top. Convexity at the top, or it is in clockwise direction. It is in a clockwise direction. So for your left hand side, the algebraic sum, the net bending net movement is in clockwise direction, then it should be taken as negative. So this is how you have to draw a bending moment diagram. So to draw a shear force and bending moment diagram, we have to draw like this. So first of all, you have to draw the load diagrams. Then you have to make calculations for shear force, and also you have to make calculation for bending moment, and then you have to draw one below the other. So load diagram followed by shear force diagram followed by bending moment diagram, clearly indicating what is a baseline, whether it is a positive or negative, and all these things you have to draw. So this is what a cantilever beam with a point load at its free end. Now we will discuss about cantilever beams with point loads. Loads, not a single load, but various loads we will discuss about. To discuss at various loads, let us take one problem, that is one numerical problem we will take, and we will try to draw shear forces and bending moment for those forces for that problem. Then we will get some idea about how to draw shear force and bending moment. Now let us see the problem first. A cantilever beam of length 2 meters carrying point loads as shown below. Draw the shear force and bending moment diagrams of this beam. So this is the question is given. So clearly this is a, if we say AD is a cantilever beam. Its total length is 2 meters, 2 meter length. So 0.7 plus 0.3 is 1.5, 1.5 plus 0.5 is 2. So this is what I think. And it is subjected to, the beam is subjected to not a single point load. There are 3 point loads. One is at one magnitude of one load is 800 newtons. The second one is 500 newtons. And the third one is 300 newtons. And all these things are acting towards downward direction. So this is what we have, shear force, and we have to draw shear force and bending moment diagrams for this beam. So how to do this such problems? First of all, we have to take the load diagram first of all, and we have to observe. So when we talk about shear forces, so let us find out, before drawing shear forces and bending moment diagrams, what we have to do? We have to find out shear forces and bending moment at various different sections of the beam. So I have divided this beam into 4 sections. See here, one is section A, that is at fixed end. Section D, that is point D, it is a free end. And in between 2 sections, that is point B and point C, where the load is applied. So these are the various points, and we will try to find out the shear forces at various points, or that is different sections of the beam. Now, shear force at D, how to find out? What is the shear force? So to left it is not there, only on this point is there. On this point also we have to find out. So shear force at this point is nothing but the resultant force at this point is only single. We are talking about right hand side of the section, or on that, from that point. So right hand we don't have any beam, and on this point we have only one force, that is one force, that is 800. Single force is there. Therefore when single force is there, then the resultant force will be that one only, 800 newtons, and it is acting downwards. So when it is acting downwards of the right hand of the section, we have to take it as a positive, that is plus sign we have to take. Now, between C and D, there is no other force other than 800. Only 800 Newton is there till C. So between C and D, the shear force is same because only one force is there, 800 Newtons only. So SF will remain, shear force will remain constant from C to D. Now, what happens at C? Exactly at C point, we will try to calculate the shear force. So there will, how many forces are there to my right hand side? Right hand side of the C, how many forces are there? There are two forces. One is 800 Newtons at D, and we have to, when we are talking about that point, and that at that point also we have to consider. So at C, we have 500 Newtons. There are two forces are there. So both the forces are acting downwards. So when both the forces are acting downwards, what will be the net resultant force towards the right side of the C section, C point? So at the shear force at C is nothing but 800 plus 500. This is the resultant force, and acting downwards, that's why I have taken it as a plus mark. 500 plus 800, it is 1300. So plus 1300 is the net resultant force, that is shear force at this section. Now, between B and C, it remains constant because between B and C, you have only the net resultant force will be 1300 only. Therefore, SF will remain constant at 1300 between B and C. Now, we will try to find out the shear force exactly at B. So, if at all we want to find out the shear force exactly at B, you have, so see how many forces are there to my right? 800 Newtons, 500 Newtons, and 300 Newtons. All these forces are acting downwards only. So, if you want to find out the resultant of all these forces, that means replacing all these three forces with a single force, what it will be? It will be the addition of all these forces. 500 plus 800 plus 500 is 1300. 1300 plus 300 is 1600. So shear force at B will be 1600. Now, if at all we want to find out shear force at A, so between A and B, there won't be any change. The same 1600 Newtons will applicable. And at A also, you will have to right side, what you will have? You have a 1600 Newtons. So if you consider the upward movement, it will be 1600 reaction. If you want to calculate the total of these three forces will be reaction. So to left side, if you want to take, you have to take this reaction. To right side, if you want to take, you have to take all these things. So we are talking about right side only. Therefore, shear force at A will be plus 1600 Newtons because all the forces to right of A is acting downwards. Therefore, this is what a shear force. Now we have found out various shear forces at different sections. Now we have to draw the shear force diagram. Here is the shear force diagram. How to draw? So we have to start with this one. The reaction, it will be 1600, that is 3 plus 5 plus 8, 1600. From A it is 1600 plus 1600. From A to B, it will remain as 1600. Now here, 300 Newton force is acting here. So we have to deduct 300 from 1600. That will be, so the shear force at this one will be 1300 Newtons. And from B to C, it will remain at 1300 Newtons only. Here, 500 Newtons downward direction. So we have to deduct 500 from 1300. So it will be 800 here. So the shear force at this point is, at section C is 800. And the shear force will remain as 800 till D. So it is from C to D, it will be 800 only. From here, 800 Newton is working here. Then shear force will change from, at D point, 800 Newton to 0. That is, it started here and you have to draw a parallel line because it's a constant. The shear force is not changing between these sections. That's why you have to draw a parallel line to the baseline to complete the shear force diagram, and it should be indicated with a positive, and it should draw above the baseline. Then only it will be positive. This is how you have to draw a shear force for the given problem. Now, we will go through bending moment diagram. Bending moment diagram for the same thing. So let us find out bending moment diagram for different sections. So we have 3 sections here, A, B, C, D sections, and we will try to find out bending moment diagram for different sections. Now, bending moment at D. Now, how to find out bending moment at D? So the force into we are talking about, when we are talking about, we always consider right hand side. So there is nothing in the right hand side, only on this you have. So at this section we have only one force, and the force how much make about this point, because it is passing through this point, there won't be any bending moment because the perpendicular distance of this force from D is 0. That's why bending moment at D will be 0. So this is what a bending moment at D section. Now, bending moment at any section from C to D, if you want to take from C to D, how to calculate? So suppose I want to find out the bending moment at C. But all I want to find out the bending moment at C. So how to find out? To my left, right hand side, how many forces are there? Only one force. Forget about the force which is passing through this point, because a force which is passing through one point, it cannot make any bend, any movement, because it is passing through that. So perpendicular distance of that force to that point is 0. Therefore, when we calculate the bending moments, we should always see how many forces are there to the right section, except the force which is passing through that point. So we want to calculate the shear force at B, bending moment at B at C. So how many forces are there to my right? Only single force is there. Therefore, how to find out the bending moment? That moment that this force will make about C, point C, is the formula is the force into perpendicular distance. We know the perpendicular distance from C. In fact, we have to find out any section. So how much distance it will have from D? How much distance it will have? Suppose it is having about C. If you want to find out, it is making 0.8. This means this force is at a distance of 0.8 mm from C. Therefore, if you want to find out, it is any section. Suppose if I want to find out a section in between here, so the force into its distance from D. So from this section, how much distance it is having, that we have to find out. Now, bending moment at C, if at all I want to find out. So 800 and X, that is distance, perpendicular distance is, distance from D is, this is 0.8. Therefore, 800 into 0.8, it is 640. 640 Newton meters, because force is in newtons and the distance is in, force is in newtons and distance is in meters. Therefore, 640 Newton meters. And the negative sign is due to hogging. As I said, hogging, you know, when we consider only this part of the section, how when a force is applied here, only imagine that only this force is there. We are talking about this force. It will bend like this, or it will make a clockwise direction. So this force is making about this point is making a movement clockwise direction. To my right side, if it is clockwise directions, you have to take negative signs, or it is called hogging or convexity at the top. See, to my right side, it is making a convex shape. Concave is this, convex is this. So concave shape. So this is a hogging, that's a negative sign. Now I want to find out bending moment at B now. How to find out the bending moment at B? Clearly, if we can see how many forces are there to my right side. right side, excluding at point B. So there are two forces, 500 newtons and 800 newtons. So how to find out how much movement this 800 newtons will make? 800 into the distance between B and D. What is the distance between B and D? It is 0.7 plus 0.8, that is 1.5. So 800 into 1.5, this is the moment that 800 Newton makes. This is negative because it is making a clockwise direction or a convexity or hogging. Again, 500 Newtons, how much it will make the moment? It makes 500 into the distance between B and C, that is 0.7. So 500 into 0.7. Therefore, 800 into 1.5 is 1200 and 500 into 0.7 is 350. Both are negative sign. So the total bending moment at B is minus 1550 Newton meters. Similarly, we can find out the bending moment at A. So if we take A, forget about the reaction because it is passing through A. So how many forces are there to its right side? There are three forces, 300 newtons, 500 newtons and 800 newtons. How much this 800 newton will make a moment about A? It is the load into its perpendicular distance, that is distance between A and D. The distance between A and D is nothing but the entire span, that is 2 meters. 800 into 2 is that one, and between how much movement that 500 Newton will make? It will make 500 into the distance between A and C, that is 0.5 plus 0.7, that is 1.2. So 500 into 1.2. Then how much movement this 300 Newton will make with about the point A? It is 300 newtons into 0.5. So this is the total. All these things make clockwise direction only. That's why we have to give minus sign to all of these things. Now the algebraic sum of all these things will be minus 1600, minus 600 and minus 150. All put together, it will become 2350 Newton meters. Therefore, the bending moment at this section will be 2350. So we have different type bending sections. At A, at D, we have seen here 0. At this section, we have minus 640. At this section, we have minus 1550, and at this section 2350 Newton meters. So whenever we want to draw bending moment diagrams, we have to find out bending moments at various sections. How to select a section? Whenever a point load is there, you have to take it as a section or a point, because at that point definitely the shear force and bending moments are going to be changed. Of course, bending moment will change throughout the span, whereas shear force, where point loads are concerned, shear force will be changed only between changed when a point load is there, and between the point loads there won't be any change in a shear force, whereas bending moment will continuously change from one point to the other point throughout the span. So this is what we have. Now we have to draw the bending moment diagram. So here we have a bending moment diagram. Now see, this is a load diagram and this is a shear force diagram already seen. How to draw a bending moment? Now we have found out the various bending moment at various sections. So at D it is 0. At C it is 640. At B is 1550. At A is 2350. We have. So when we have these things are there, and below the baseline we have to draw. Why we have to draw the below the baseline? We have to, because it is a negative sign. Clockwise direction we have to take in the right section, right side of the section. Clockwise direction we should always take it as a negative, because it is making a hogging or a convex shape. So convexity, when the top is there, we will take it as a negative. It is a sign convention. In the fundamentals, we have gone through that. Now this is a C point, this is a B dash point, and A dash. A dash, B dash, C dash will indicate the bending moment points at that particular section. So how to draw? We have to join with a straight line because it follows a straight line. Why it is follows straight line? Because it is a W into X, weight into distance. So it is similar to the straight line equation, y equal to mx. So like that. That's why X is variable. Here the bending moment depends on the distance from the free end. Therefore it is 0 to 600. We have to draw a straight line. From 600 at C to 1550 at B, we have to draw one more straight line, and at B to A, we have to draw, and finally we have to join this one. So this is a bending moment diagram of particular section. So this is how you have to draw, and we have to draw after calculation of all these things. First of all, we have to draw a load diagram, and below that we have to draw shear force diagram, and below that we have to draw the bending moment. Whenever we are drawing these forces, you should see that all these points coincides. See here, A point is coinciding for both the three diagrams: load diagram, shear force diagram, bending moment diagram. And also here B point coincides here, and C point coincides here, and D point coincides. It's like that. You can't draw shear force at one particular place, bending moment at other place. You can't draw. You are not supposed to draw. A good convention is you have to draw the bending moment shear force diagram just below this one. So this is how we have seen. Hope you have gone through the fundamentals of shear force and bending moment diagram at a point load. So whenever we have a point load at a free end, or whenever we have point loads at different places, so we have to see that the bending moment diagrams and shear force diagrams, before drawing them, we have to find out the shear forces and bending moment at different places. And as far as the cantilever beam is concerned, cantilever beam, in the cantilever beam, the shear force will make point loads. Point loads are, as far as point loads are concerned, you have a constant between the point loads. So whenever point load is there, the shear force will change. Between the point loads, the shear force won't change. It will remain as constant. Whereas bending moment, it will continuously change from one point to the other point, because it follows the straight line, law of straight line. So this is what we have. Hope you have enjoyed this shear force and bending moment. And in future, and in the next session, we will try to discuss about shear force and bending moment diagrams for UDL. UDL means uniformly distributed load. In the uniformly distributed load, the load is not a point load or concentrated at one particular place. It is entirely distributed the entire span. So uniformly distributed. For such type of things, how to draw shear force and bending moment diagrams, we will see in the next video, that is cantilever beam with UDL. If you like this video, please share with your friends, and subscribe this channel. And this video is very useful for, especially for engineering graduates of both mechanical and civil engineering, and also for diploma holders. This video is specially made for diploma holders, especially diploma in mechanical engineering students, as well as diploma in civil engineering students. So hope you enjoyed. Thank you for viewing this video completely, and if you like it, please share these things with your friends and subscribe to this channel. Thank you, one and all.